Okay, so welcome back. In this particular video, we're going to be talking about compound interest. I'm going to break this video up into a few segments. One will be deriving the formula, another will be using the formula with different compounding periods, and another one will be sort of finding the different values that sort of occur in the compound interest formula. And then we'll take a look at compound depreciation. Okay, so first things first, right? We all would have seen at this stage, if we're in this course, the compound interest formula: A equals P outside of 1 plus R all to the power of N. Okay, so basically this A here stands for the final amount in the account, right? And what you'll often see used here is this is often called the future value of an investment. Okay, so that's the money that is built up right at the very end of your time period, and you're investing after you've invested everything. Right, this here, it's exactly like simple interest. Okay, except we often call this not only the principal, but we also often call this the present value. So the money that we are starting off with, our initial investment. Okay, again, just like before, this is our interest rate. Okay, and we must remember that we put it as a decimal whenever we put it into this formula. And finally, this N here refers to the number of time periods. In this particular case, we're talking about the number of compounding periods that sort of occur, right? And so this is just like the other one, the number of time periods. Okay. Now, I've got a note here just to sort of tell you about the fact that our compound interest, when we're using this formula, it actually follows a recurrence relation. Now, you've probably heard recurrence relation when we've been talking about geometric sequences and series. Okay, and I'm going to show you that compound interest actually follows the pattern of a geometric progression. Okay, I'll show you sort of where that comes from. Now, understanding visually what's happening with compound interest is also another important thing. Remember, when we had simple interest, when we drew the graph, it was just a straight line. Okay, but when we're compounding, the value of our investment actually climbs at an exponential rate. Okay, an exponential rate. So it's actually worth us to grow an investment using compound interest, and it's also the main type of interest that's used in everyday life. Okay, there are very few applications that use simple interest. So in this first little segment, we're going to take a little bit of a look at how we actually derive the formula, and we go back, this particular formula here, and how we go back to basics using a recurrence relation. And then next example, I'll show you how to use the formula itself. Okay? Okay, so this is an example that I'm going to show you where the formula actually comes from. So I'm going to use some numbers, not just straight algebra, to sort of make it easier to sort of work with and to show you a little bit of a relationship that happens as a geometric progression. Okay? So Patrick invests $2,000 at the beginning of the year at 6% per annum, and it says to find a formula for the amount in the bank at the end of N years. Now, we're going to assume that the interest is compounded annually, okay? Right, and what we mean when we talk about compound interest is that we take it out of the account at the end of the compound period, and rather than like simple interest, we keep it in our pocket, we actually put it back into the account and it becomes a new principal, okay? Again, you've probably seen this used before, so the concept should be familiar, but you may not have seen it as a geometric progression, okay? So first things first, we're going to use this formula, all right? So amount at the end of each compounding period was equal to our principal at the start of that compounding period plus our interest. Okay? So we know what our principal is. Okay, the principal is relatively simple. It's equal to 2,000. It's our present value that we start off with. And our interest rate, I, is equal to 6%, which as a decimal is just 0.06. Okay? Now, in terms of our time period, we don't really know what's going to happen with N years. So we're just going to do repeated applications of simple interest just to sort of figure out our pattern that's sort of going on, okay? Right, so each time period is sort of only going to be in there for 1 year, okay? So essentially, the amount at the end of the first year, right, is going to be equal to our principal, which is 2,000, plus our interest that we generate on the principal, which is our interest rate multiplied by our principal, okay? So that's 2,000 times by 0.06. Now, let's do a little bit of tidying up here, right? And just collect some common factors, okay? You'll notice there's a common factor of 2,000 here, so I'm going to drag the common factor of 2,000 out the front. So that's 2,000 outside of 1 plus 0.06. And I'm going to come back to this sort of thing just up here, this particular step up here. All right, but let's just simplify it now for the moment, okay? So that's equal to 2,000 now. If we simplify the inside of the brackets outside of 1.06. Okay? All right. So that's the amount after the first year, right? So let's now find the amount after the second year. With compound interest, we take whatever interest we generate and we plug it back in as our new principal. So for our second year, this thing here is our new principal for our second year, okay, rather than starting off with 2,000, whatever this amount is. I know we could simplify it, but I want to establish the pattern here for us. So amount 2 is equal to our principal, 2,000, 1.06, plus our interest. So it's our principal, 2,000, 1.06, multiplied by our interest rate, which is 0.06 here. So 0.06. Again, you can probably see a common factor emerging, and you'll probably pick up this pattern really, really quickly. Okay, the common factor here is 2,000, 1.06. Outside of, we're left with a common factor of 1 here. If you're not quite sure that you can see it, there's just a times 1 there that we haven't written. Okay, and a 0.06 over here on the side. So 1 plus 0.06. All right, let's tidy that up. Okay, it's equal to 2,000 outside of 1.06. 1.06, which just leaves us after simplifying using some powers. It's 2,000 times 1.06 squared. Now you might be starting to notice a little pattern here already, and that's great if you have. I'm going to show you one more time where this is going to pop out from. Okay, so now let's do it for our third year. Okay, this is going to become our new principal because we take our principal amount and insert it back into our account at the end of the second year. Okay, at the start of the third year, my apologies. Okay, so our amount 3 is going to be equal to our principal, all right, the amount that we had at the end of year 2, all right, which is 2,000, 1.06 squared, plus our principal times our interest, right, which will give us our interest generated on that particular year. So 2,000, 1.06 squared times 0.06. Just like last time, you'll notice immediately that we're going to have another common factor. Okay, the common factor is 2,000, 1.06 squared. All right, and what's going to happen is we're going to be left with a common factor of 1 on this particular first term. I'm just going to take some steps and shortcut this down a little bit, skipping some of the steps in between here. So we're going to be left with a common factor of 1 plus 0.06, which in this particular bracket will give us another 1.06, just like what happened up here in this step. Okay, so simplifying that down, we end up with 2,000, 1.06, all to the power of 3. Now, you're probably starting to already recognize a pattern here, okay? All right, we could make a prediction. You'll notice here that whatever number occurs here also occurs in the power. What is in the brackets isn't actually changing, and neither is the number out the front. So for us to find a formula for at the beginning, for at the end of n years, right, we could make the prediction of an is equal to 2,000 outside of 1.06 all to the power of n. Now let me just show you where this actually sort of comes from, right, and how it relates to our initial formula of the compound interest. I still haven't shown you where the geometric progression comes from, but I will show you that in just a moment. Okay, so you would agree that this is equal to our principal times, inside this bracket here, it's equal to 1 plus our interest rate. Okay, now remember I told you that this was going to come back to this particular step up here that I highlighted, right? It's equal to 1 plus our interest rate, okay, inside of this bracket, all to the power of n. And that there is our compound interest formula. That's the easy way of understanding it, but how does this actually relate to geometric progressions? Well, I'm going to show you. Okay, so let's see how this actually forms a geometric progression. And rather than making a prediction, we actually show mathematically that's what the formula pops out to be. Okay, so at the end of the first year, we had this amount. At the end of the second year, we had this amount. At the end of the third year, we had this amount. Okay, and that would continue on in the same pattern. We could show it mathematically. We want to go A4, A5, A6, and all that sort of stuff. But we're not going to, okay? Let's just say that I wanted to make a formula for the nth term the nth year of this particular sequence. Okay, you need to ask yourself whether or not it's going to be a geometric or arithmetic. My apologies. Okay, and you'll notice here that it's actually a geometric sequence, right? This here is our first term, so a is equal to 2001.06. And then to go to each next term, we're multiplying by the same common ratio r. That particular common ratio you can identify here as being 1.06. So 1.06. Now, just for you to understand how this works as a geometric progression or sequence, we need to remember the nth term formula. Tn is equal to a outside of r to the n minus 1. This is why you need the knowledge of series and sequences before you sort of approach this topic in this particular mindset. Okay? So, to find our nth term or our nth year value, we just put in our values. 2001.06 is our a value times r, which is 1.06 to the n minus 1. Now what happens is that we have this 1.06 to the power of 1. So because these two things are the same base, we multiply them together, the power, and I'll just write this in blue off to the side, becomes n minus 1, adding the powers using our index laws, plus 1, which is equal to n. So if we simplify this down, our nth term formula is 2000 outside of 1.06 to the n, which is exactly what we had before. I showed you how this is equal to our 1 plus r, this is equal to our present value or principal, this is equal to our time periods, and this Tn is actually equal to our a value. So that's how you establish the compound interest formula using a geometric progression, and that's why it works, okay, rather than taking a guess and a stab at the pattern. All right, so in our next couple of videos, I'm going to show you how to use the compound interest formula and to find all of the values inside of it, okay? There's a couple of different steps that you need to know and just to practice with different compounding periods as we move along. Okay, thank you very much.